Thank you very much for your nice introduction, and thank you very much for having me. I'm very happy to be here and visit your group because like you have done so many great work, and I think in terms of topic, it's also very relevant. Yeah, okay, let me start with my presentation today. So I'd like to share our recent work towards learning a driving simulator from the real world. So why are we interested in learning a driving simulator? So autonomous driving, of course, has a very large market, and many big companies, they are working on this. And this is like image like from Waymo that like they are testing their cars in the real world. And of course, this is very common for autonomous driving vehicles that they test their algorithms in the real world. However, in this case, you see that we need security drivers sitting on the car, and still this cannot be very secure. So another alternative is that can we build, for example, a simulator that enables training as well as evaluation in such a like in a synthetic world, which means there will not be any issue for safety. But of course, like this is one of the most popular autonomous driving simulator that is commonly used, called Color. And of course, you can see that like such simulators still like there is a clear domain gap between the simulator and the real world. So even if we have a perfect autonomous driving algorithm that can drive perfectly in the simulator, it's not guaranteed that it can transfer to the real world without any issue. And another issue with the simulator is that like currently those 3D assets, they are created like manually by artists. And creating those 3D assets actually are quite expensive and time very time consumption. For example, like creating such a car with many details will take like 3 hours even for an expert. So it's not really affordable to create such 3D assets. And then recent advance in neural rendering like really gives us it really gives us a very promising direction that maybe we can actually build a simulator from the real world that has no domain gap, and like the assets are easy to obtain. And of course, this is like pioneering work in this direction is NERF that we all very familiar with. And this, maybe you can guess whether it is a real captured video or it is rendered by NERF. If you look closely, you can still observe that it's actually rendered by NERF. Actually, this is a result of InstantGP. But actually the quality is already quite impressive, and it's not that easy to tell like the difference from the real world video. So can we build a simulator from the real world using neural rendering techniques? So let's think again, like for manual design, what the advantage we have is that it's fully 3D controllable, and it has perfect 3D labels as well as 2D labels, as we have seen in this color example that it provides per pixel accurate semantic and instance labels, which those labels are important to train and also to evaluate autonomous driving algorithms. However, there's domain gap between the real world, and it's expensive to create. Then for neural rendering, of course, there's no domain gap and there's no design effort. You can just take a camera to drive around and you can collect the video for reconstruction. However, there are also like many limitations that like really make it an autonomous driving simulator. For example, like if we simply reconstruct the world based on the collected videos that we have, then we may have limited control in viewpoint. If you want to turn left or you want to turn right, then maybe you observe artifacts. And also there is no semantic if you directly collect the video. So we do want to provide semantic information to really enable training or evaluating autonomous driving algorithms. And of course, like originally NERF renders in a very slow time, and this also like limits its real application. And furthermore, it actually depends on ground truth camera poses as well as like the dynamic poses of the cars. For example, if the scene has dynamic cars, usually like autonomous drive, like the rendering algorithms, they require the ground truth of the dynamic vehicles to be able to reconstruct the scene, and those are also not easy to obtain. And finally, there is also lack of novel content, right? If we simply reconstruct with what we have already observed, And then we train an autonomous driving algorithm on this thing. Maybe it will just all fit to the thing that we have. And it will also not really transfer to the real world. And of course, there are many more, but I will try to cover some, of this our work and try to address some of the challenges here. And firstly, let's begin with the question, what dataset and benchmark do we need? And we believe that the KD360 dataset is actually a very good one for this purpose, that we want to build an autonomous driving simulator from the real world. The reason is that we do have dense semantic and instance annotations in both 2D and 3D space. So KD360 is the dataset that I built since my PhD. I actually spent 5 years on that to finish the full project. And we do have like the densely annotated bounding boxes for the entail city. And then we transfer those 3D bounding primitives to the 2D space to be able to obtain like semantic and instance label for every 3D point and for every 2D pixel. And furthermore, we have multi-sensors with good coverage in the sense that we have like fisheye images to cover 360 field of view. And we also have well-calibrated intrinsic and extrinsic parameters. And in terms of benchmark, we have like, we were thinking like with this data set with dense annotations, what can we advance the field like on top of Kitty? So this is one of the benchmarks one of the new benchmarks we proposed named Nova View Semantic and Nova View Appearance and the Semantic Synthesis. So in this benchmark, the goal is to giving post sparse images with like the users to submit their RGB images and semantic labels rendered at Nova View points. So this aligns well with the target for being able to render at Nova View points, as well as being able to providing the semantic information for a simulator. And one thing to mention here is that we, in the original KD360, the 2D labels we provide are obtained by the automatic algorithms that we use to transfer the 3D that are transferred. The 2D labels are transferred from the 3D space, and those may not be very accurate. And for this benchmark, we then manually annotated all the 2D ground truths to be able to evaluate algorithms. So given the data set, now what we can do to build a simulator from the real world, we actually worked on two directions. One is on reconstruction and one is on generation. And the task would be that for the reconstruction, the task would be giving the post RGB images. Can we render semantic and RGB at novel viewpoints? And for the generation, we then focus more on can we generate novel contents. And let's begin with the reconstruction part. So this is one of the earliest work we did in this direction named panoptic nerve. In this work, we aim to infer semantic and instance label in the 3D space to obtain 2D panoptic labels while volume rendering. So it's quite straightforward. And also like for this project, we actually started from easy tasks in the sense that we do assume that we have quite a lot of information that are available. So on top of the sparse images, we do use the coarse 3D modeling primitives provided by the KD360 dataset. And then we further assume that we have some noisy 2D predictions provided by some existing perception models. So it's kind of like an easy setting in the sense that we do have 3D and 2D information and we just need to fuse them. And actually, it's not super trivial to obtain like very good results, even given those information. So one of the reasons is that NERF actually fails to recover good geometry given those sparse street view images. And this is the depth map rendered by NERF. And we can see that there are many artifacts. And if you simply then apply the semantic based on the 3D coarse 3D bounding primitives, then you will have artifacts because of the poor geometry. For example, like in this region, like in this region, it's labeled as tree because those region has some floating points that should not exist. That's the error in the geometry leads to the error in the rendered semantic label. And of course, there's another challenge that the bounding primitives, they are very coarse, such that they have intersections, which means they have label ambiguity in the intersection of the bounding boxes. For example, like this region is annotated by both the bounding boxes and the road. And in that case, it's hard to really tell which label it really is. So those also leads to like the artifacts. And if you simply use the 2D annotations like semantic nerve did, we also observe that denoising the 2D predictions is very hard, given the bad geometry, as well as the predictions themselves, they are very noisy. And actually, this is the method we use in the KD60 paper, that we use a classical a graphical model to infer the label in both 2D and 3D space. And actually there we do require to reconstruct the scene first based on a classical reconstruction method to determine which point is visible when it is projected to the 3D space, to the 2D space. And in that case, it still suffer from inaccurate reconstruction. And in panoptic nerve, we improve geometry guided by the semantic information. And this is the depth map that we obtain. And this is the result that we obtained. So it actually performs better than the previous methods that I mentioned. And also is able to render panoptic labels. So let me give you a brief overview of the method. So we actually, this is the method of follow-up work, which we named Panoptic Nerve 360. So the key is that we now integrate further the fisheye images to be able to cover large viewpoint changes. And but overall structure is very similar to the Panoptic Nerve. The key is that we now have like this design of dual semantic fields. And we also have like a fixed instance field to determine the instance ID of every point in the 3D space. So why do we have such like dual semantic fields? One of them is the 3D bounding annotations that we have. And the other is a neural network that is learned similar to semantic nerve. So the key design difference comparing to semantic nerve would be introducing this additional fixed semantic field. And why do we need this in the framework? The idea is that we can actually leverage this fixed semantic field to optimize the geometry of the underlying geometry. Because if we apply a loss here, like we render the 2D label based on the fixed semantic field, then it can only update the underlying geometry to update the rendered image here. So this actually leads to improvement in the geometry. And furthermore, we also, in this Panoptic Nerve 360 work, we also introduced like to use also to improve the boundary between the instances based on this simple prior that the buildings are actually usually separated by lines. It's basically a Manhattan assumption that Manhattan world assumption that the buildings, they are actually like usually planar objects, and then they can be easily separated by lines. And we further add, like based on initial rendered panoptic label, we apply linear regression to get this line boundary. And further, we use this to supervise again the rendered panoptic labels. And this also backpropagates to the density to improve the geometry between two buildings. And in that case, we can actually lead to we can actually learn better geometry supervised by the semantic information. But this does not address the ambiguity of the 3D bounding primitives. So you still have like you still have to determine which semantic label it should be when it is included in two primitives with different semantic meanings. And that's why we still need this learned semantic field here to determine, to avoid the ambiguity, to address the problem of the label ambiguity. And in this follow-up work, we further incorporate fisheye images for 360-degree appearance and label synthesis. So here we render both perspective and the semantic, the fisheye images. And another design choice we have here is that we actually figure out, in order to model both the appearance and the semantic label effectively, it's better to combine a hash feature with the deep MLP. So what we observe is that if you simply use a hash feature for reconstruction, then you can get very good appearance, but actually it leads to more artifacts in the semantics because of the high frequency or the hash conflicts. And MLP, they actually provide a smoothness prior or a smoothness bias to list better semantic or remove the noise in the semantic prediction. However, it does not really lead to very good appearance. So we observe that the combination of the hash feature and the MLP feature leads to the best performance in both appearance and semantic. So this is the result we have in Panoptic Nerve 360, that we are able to render panoramic panoptic label and semantic label, as well as appearance and depth. And now we are also able to render like enable 360-degree camera rotation. Of course, the side views, they are not as good, but the results looks plausible. And this is the comparison for our instance building refinement. So we can see that without the instance guided geometry optimization, the boundary between two buildings, they may not be really good. But with this simple prior, it actually leads to quite sharp instance boundaries. And of course, that's one of the preliminary work we did, and there are still quite some limitations. First of all, it actually requires quite some input information. It requires ground truth camera poses, and it requires annotated 3D bounding primitives for the static regions. And even though we do not consider dynamic objects, if we do add dynamic objects, we will also require dynamic 3D bounding primitives for those moving objects. And furthermore, it consider only like around 100 meters consider only like about very small region of the scene. And how can we scale up to larger scenes? That's also one question. And further, we still need to speed up the rendering, because like the previous works, they use the large MLP, which slows down the rendering. So I will quickly go through two of the follow-up works that we did. The first one is towards large-scale mapping with joint post optimization. Is work that we did we submitted to RAL. In this case, we consider to use LiDAR scans as input. And furthermore, we do not require the ground truth poses. We directly use a LiDAR odometry algorithm to predict the poses between two LiDAR frames. And we aim to reconstruct such a large-scale urban scene. And here, what we found as a key challenge is that if you do not use ground truth poses, what we normally do is that you do SLAM, right? You do like joint pose estimation and mapping. And in that case, if you do SLAM, if you're familiar with SLAM, then we have like in odometry, when you detect a loop, you will need to update the poses, right? But in that case, if you use simply like a global scene representation, like a large MLP, in that case, if your poses are updated, then you need to retrain the full MLP to be able to adapt to the new poses, right? So the challenge would be that the global scene representation requires retraining with the detected loop. And then we propose this idea of using multi-volume feature fields, as well as the optimizable relative poses to represent the large scene. And then based on the detected loop, we can simply update the relative poses of the feature volumes to make it like fast, like to quickly update to the target pose. And the idea is quite straightforward. And we actually then apply, based on a detected loop closure, we actually apply we actually optimize the pose based on scan to volume alignment. So it's actually then quite easy. So if we detect that there should be a loop, then you can, based on this current LiDAR scan, you should fit to the reconstructed feature volume, and we actually fix the reconstructed feature volume and optimize the pose to let them fit. And in that case, you can lead to good loop closure performance. So this is the demo that we have on the KD360 dataset. So this is a pure LiDAR-based method. So the RGB images are only used for visualization. And this is the reconstructed normal, and below is the reconstructed semantic. And here we see that the model can actually scale to a large scale easily, and also it can quickly adapt to the loop closure. I think there will be a loop here. Yeah. So that's the work towards scaling to large scale things. And then let's go back to the other challenges about like, how can we get rid of ground truth bounding boxes as well as speed up the rendering. And this is one of the latest work that we did, trying to apply 3D Gaussian splatting to urban scenes, which is also quite straightforward. And the key here is that we actually want to leverage only RGB images instead of relying on ground truth annotations. So what we take as input is the post RGB images as well as noisy 2D and 3D predictions. For the 2D predictions, we used optical flow semantic. And for the 3D predictions, we leveraged the 3D trackings of dynamic objects. And this allows us to remove the dependency of the 3D ground truth bounding boxes of static and dynamic objects, and also enables fast rendering at 100 FPS. That's due to the representation of Gaussian splatting, of course. And this is the whole pipeline. And based on, we extend 3D Gaussian splatting to model camera exposure, optical flow, semantics, and dynamic objects. And the key here would be this part that we actually add physical constraints to the dynamic object pose estimation via a unicycle model, which actually, I will show later that it actually improves the performance, because if you simply optimize the poses of the dynamic objects individually, it may converge to some local minimum. But actually adding such like a very simple physical constraint that the car should move following a unicycle model, which it should be a more advanced model, but actually we found that the unicycle model already works quite well. And we, with this method, we demonstrate state-of-the-art performance using noisy 3D bounding boxes as input. The 3D bounding boxes we use are predicted by some existing algorithms based on the RGB input. And we do have comparison to the baselines. And for example, on the synthetic data set, we then manually add noise to the bounding boxes. And we see that existing methods that fail in this case, and our method can actually reconstruct the car like quite good, despite that the bounding boxes are pretty noisy. And we also ranked the first on the KD360 Nova Business leaderboard with Gaussian splatting. And I'd like to show you some more like ablation study to give you some bit more insight about the unicycle model. For example, like here, we show if we simply, without any optimization or without the unicycle regularization, then of course the reconstructed or dynamic objects will not be reasonable. And if we simply optimize the bounding boxes without the unicycle constraint, then it is improved based on by comparing to without any optimization. But actually the bounding boxes, they are not really they converge to some local minimum, and the reconstructions are not really sharp. And our method actually leads to like quite convincing performance. And here we show the initial bounding boxes that they are very noisy, and it's actually much noisier than usual than the 3D bounding boxes that you will get from a predicted one. So here we add quite some strong noise here. And after optimization, you can see it actually forms a reasonable, very reasonable trajectory based on this unicycle constraint. And another interesting finding is that incorporating the semantic information actually helps us to improve the underlying geometry, only if you apply the softmax in the 3D space. So there are two options to render the semantic label. One is that you apply softmax in the 3D space, and such that each point is already normalized in 3D, and then you accumulate them, right? And the other choice is that you accumulate the logits, and then you apply the softmax in the 2D space. And what we found out, like the later case is actually what is commonly usually used in semantic nerve and existing nerve-based methods. And in that case, the model can actually cheat by adjusting the scale of the logits. So it does not really improve the geometry. But if you then apply the normalization in the 3D space for each 3D point, it actually improves the geometry like this. So on the left, those are the centers of the 3D Gaussians. On the left, we show that they can be very noisy if you directly use the 2D normalization. And those are actually also the Gaussian centers if you do not add any semantic information, if you use only pure RGB. And if you then use the semantic, incorporating the semantic information and applying the softmax in 3D space, the 3D reconstructions actually looks quite plausible. And we also show that the flow supervision further improves the geometry, which also makes sense because flow actually provides dense correspondence between two frames. And this also allows us to further improve the depth. And those are the scene editing we have, because we also disentangle the dynamic objects from the static ones, so we can enable scene editing, and as well as viewpoint extrapolation. And of course, we do inherit the advantage of Gaussian deviating that we can now do real-time rendering. And the thing to notice is here is that despite that we have incorporated many components like rendering flow or depth or semantic, it does not really slows down the rendering speed. So we can still render at about 100 FPS. Okay, so a quick summary for the reconstruction part. I introduced panoptic nerve 360 for panoptic reconstruction, and there we considered a rather simple setting that we do have a lot of information. And then for NF Atlas, we scale to large things and without ground truth poses. And then we further explored to use Gaussian splatting for real-time rendering and also removed the need of 3D annotations. Some take-home message here. We do observe that the semantics can improve geometry with proper architecture design. And the required input can be reduced to unposed images, which means that the pose can also be jointly optimized. And lastly, physics constraints, they can be beneficial when incorporated in the optimization. Okay, so that's about the reconstruction part. Let's move on to the generation part. And the previous works, we focused on reconstructing the existing word, but it's also very exciting that we are able to generate novel contents and put them in, for example, into the simulator as well. So this is one of the earliest work that we did a graph, and we basically extend GANs to model 3D assets by lifting the generator to the 3D space. So this is a 3D aware GAN by lifting the generation to 3D space in combined with rendering. And it enables generating unseen objects by sampling from the noise distribution, as we show here. And of course, there are many follow-up works in this direction, including the Vox graph that we did, and also the very well-known EG3D. So we can see that all of these works, they consider simple objects with non-camera pose distribution. For example, like cats or human faces, like where the camera pose distribution is fairly easy to be obtained. So the question we ask here is, how can we learn 3D aware generative models from unposed in the wild images, as well as scaling up to articulated objects and complex scenes? So for the first question, for 3D GAN from in the wild dataset, why do we want to address this question? Its motivation is also very straightforward, because the camera pose is actually unknown for many in the wild objects, like this complicated car dataset here on the left, and also like such elephant dataset on the right. There is simply no algorithm that can extract camera poses from those images. So and we have like an ongoing work on this direction, so I'm not going into the technical detail, but I'd like to show you the results that we have. So here we jointly estimate the camera poses of each real image, and then the 3D generative fields. And in that case, we can really like learn the 360 generation in the canonical space, and because we do have fairly good camera pose estimation. And this allows us to produce the results on the right, well, whereas the baseline fails to reconstruct the full object. And then like humans are also very important in the autonomous driving things. And that's why we also worked on human generation. And I know that you also have the very good work on this direction. And the key challenge we would like to address here is that now we need to fuse multi-view information across different instances as well as human poses. So we do assume now the camera poses are given as well as the human pose distribution that are inferred from some existing methods. Because like for humans, like those, we do have such algorithms to predict the camera poses in fairly good accuracy. And yeah, here actually at the time we started the work, we think it is indeed a concurrent work to EVA3D and others, because at the time we started the work, there were no such methods, but like many of them came out in that year. And here is like my take on the difference of these different algorithms. For example, like the very first enough work, it uses it learns such a blend ways to map from the word space to a canonical space. And actually this does not really generalize us very well. Then other methods like GNAF and AvaGen, they use a deterministic mapping to map from the word space to the canonical space. So this actually leads to better generalization because it's deterministic mapping, but actually it leads to some ghosting artifacts when a point in the free space is mapped to some occupied region in the canonical space. And for EVA3D, it's actually like what we tried is very similar to EVA3D, that we do not really require a single canonical space, but we map to several local coordinates. And it actually leads to very good generalization and also removes the coding artifacts and also very high quality. And but what we observe is that for EVA3D, it's sometimes very occasionally it leads to mixed local semantic meaning. For example, like because you do map, for example, like the hands into the like sometimes your hands are putting like next to your body, and then sometimes your hands are also generated in the body. So that's what we observe, but very occasionally. And yeah, so what we did is actually very similar in the idea of mapping to local coordinates, but we used a more fine-grained local coordinate system based on the vertices of simple. And this also allows for good generalization and removes ghosting artifacts. And also because we do have this fine-grained coordinate system, this allows us to preserve the semantic information better. And additionally, we show that we can perform party control. And the idea is quite straightforward. So the whole architecture is actually inspired by point nerve, that we can represent the features in the 3D space based on a predefined set of points. And for humans, it's actually quite easy that we can directly define such points based on simple. And then we build such a generative vertex-based radiance fields using the simple vertices. And then each sample point is mapped to the local coordinates of the k nearest neighbor vertices. And then we use 2D CNN to generate the vertex features that is efficient to be generated. And further, we use the weighted average vertex features as well as the local coordinates to map it to color and density. So afterwards, we are able to obtain part level control for free if we simply apply PCA to the vertex features. And these are the part control results. Like we can manipulate the head, the upper body, or the lower body individually. And here is the more results about like viewpoint control. And of course, we still struggle to achieve the same quality as EVA3D, which is, yeah, I think that's like really hard to beat. And we show like appearance control as well, like where we interpolate in the latent space. And here we show part control. where we apply like control to the head, to the upper body, and to the lower body individually. And here we show that the method can actually generalizes quite well to unseen poses. So the so the model is trained on the deep fashion data set, and then we transfer to S++ poses where they perform dancing and actually performs reasonably well. And the last topic I would like to cover today is that then how can we really scale up to scene level generation? So those are object level generation. And for autonomous driving, we really want to scale to scene level. And there are also existing works in this direction like Giraffe and Discosing. They consider compositional modeling, and they model the foreground objects in the canonical space. And however, they do not really model the geometry of the background. And you show in the demo, they have this static background. And if you simply change the camera pose, then the background just changes all the time. It's not really consistent because they do not really model the background. And in our urban giraffe, we propose compositional and controllable synthesis for both foreground and background, in the sense that we are now able to move the camera in the scene, like driving forward, and as well as editing the foreground objects. And what's also cool is that now we can edit the semantic meaning of the background. For example, like changing a building to a tree in this case. So the idea is then also very straightforward because it's really hard to learn the geometry of the background directly from street view images, from a number of street view images. It's not like for object generation that you have a canonical space to generate objects, right? So in this case, we simply introduce a panoptic prior for the coarse geometry and semantic guidance. And this geometry prior is provided by the KD360 dataset again. Like we simply voxelize the 3D bounding box annotations to obtain such prior information. And here is the method. Firstly, we split the prior into semantic volume as well as the object layouts. The semantic volume, both of this information is provided by the KD360 dataset. And then we have this compositional architecture that we split the scene into sky, stuff, and objects. And for the objects, is generated similar to giraffe, like the objects are generated in the canonical space. And then for the stuff generator is like a 3D convolutional neural network that's conditioned on the semantic voxel grid. And for the sky generator, it's simply a 2D generator that's generated in the infinity far away. Further, we similar to EG3D, we perform neural rendering at lower resolution and use we perform volume rendering in the lower resolution and use neural rendering to upscale it to higher resolution. And for training, we have the adversarial losses for the full image and as well as for the object patches. That design is also similar to discosing. And furthermore, in this work, we have reconstruction loss for the stuff regions, which we observe stabilize the training of the 3D GANs. But actually, in the follow-up work, we observe that this is not necessary, and removing this actually leads to better quality. And this is the result of urban giraffe. And we can see that now we're really able to move the camera in the scene, and we giving a semantic layout, we are able to generate plausible city scenes. But actually the quality is not that great. So we are still working on this. So I would like to show you here what's cool about is that we can change the semantic meaning of the background, like turning the buildings into tree. And here is one of my favorite, like that you can change the semantic meaning of the road, like changing the road to grass. Okay, so then I'd like to share you some of the follow-up work in this direction. Like we are extending it to really improve the fidelity of the rendered scenes. So this is the follow-up work of urban giraffe, and now we do. I'm like more confident about this current result that we really achieve higher quality. And with this generated 3D scene, you are able to change the camera viewpoint, like turning to the left and to the right. As well, you can also render the depth maps as well as the semantic labels based on the generative model. And we can also do latent interpolation, like here, that we first manipulate the latent of the background and keep the foreground fixed. And this part is about interpolating the foreground. You can see the colors of the car are changing. And this is a simple fly through after the interpolation. And we can also perform object editing. And here in this follow-up work, we also improve the quality of the generated foreground objects. Now they look more plausible. And we are also working on extending this to other data sets like Waymo. And this is still preliminary results, but yeah, it's the idea is that this idea can also be scaled up to other data sets like Waymo or new things. And here is also results on Waymo. We show latent interpolation. Yeah, so that's all for the generation part. As a summary, here we briefly introduced our work for the in-the-wild 3D aware object generation, as well as a very 3D for controllable 3D aware human generation, and the urban giraffe for controllable 3D aware scene generation. The take-home message here. So for 3D generation in canonical space, it is important if you have only 2D supervision, right? Because we do need a canonical space to be able to fuse the multi-view information from the entire data set. This really then enables learning good geometry. But for example, like for urban things, then it's very challenging or even not possible to define a canonical space. And in that case, it's really important to have some coarse geometry guidance to enable the learning of the generative model when a canonical space is hard to define. Yeah, so that's all the work that I want to share. Of course, like towards really a driving simulator, that's not enough, right? So there are still one of the many more future work that we aim to explore. For example, like we would like to enable more diversity, like cross data sets or like busy traffic scenarios, and also like integrating the generated pedestrians into the scene, and also generating some adversarial cases for autonomous driving. And then furthermore, controllability, like controlling the weather and lighting more explicitly. And what's also very important is that we enable, like really make it useful for autonomous driving algorithms, like improving autonomous driving perception or control or planning algorithms. And the last thing is that what we also discussed during lunch, right? So now giving that thorough is like so impressive. We are also thinking like, do we really need 3D, or is like 2D video diffusion the answer to this, right? So I think this is an open question, and I'm happy to take any questions. And thank you very much, and thank my collaborators. Thank you.